identifying different types of stress and related cracks using thermal imaging. Have you ever wondered why machine components fail? Or how to spot the warning signs before disaster strikes? Imagine having the knowledge to catch potential failures early, saving time, money, and maybe even the machine itself. In this video, we'll dive deep into the types of stress that impact machine components, explore the different types of cracks they leave behind, and reveal how to use thermal imaging to visualize these hidden threats. Stick around, because by the end, you'll know exactly what signs to look for to keep your machines running at their peak efficiency. Stress is the internal force per unit area within a material caused by external forces, uneven heating, or permanent deformation. When materials respond to this stress by changing shape, that change is known as strain. Essentially, stress measures the intensity of force acting on a material, while strain shows how the material responds to that force. Stress is the cause, while strain is the effect. Imagine a component subjected to stress, whether from mechanical load, thermal conditions, or environmental factors. Over time, this stress can impact the material's structure, gradually wearing it down. But how likely is it that this component will fail? This likelihood, or probability of failure, depends on a few key factors. First, the material's strength. Some materials are naturally more resistant to stress than others. Then, we have the intensity and duration of the stress. Higher or longer applied stress increases the chances of failure. Finally, environmental conditions play a role, such as temperature, humidity, and exposure to chemicals, which can accelerate deterioration. We often represent the probability of failure in a curve. Early on, when stress is light or occasional, failure is rare, but as stress builds and time passes, that probability grows, especially if maintenance or inspection is lacking. Understanding these stress factors allows us to estimate when a component might fail, helping us take preventive action before breakdowns occur. 5 types of stress. Let's break down some key types of stress that materials face under various forces. Think of them as the pressures and pulls of the material world. First up, compression stress. This type of stress is like giving a material a tight squeeze. When compression stress is applied, it reduces the volume or shortens the length of the material, kind of like how a sponge compresses when you press it down. An object under compression stress, such as a shaft or a roller, will begin to exhibit buckling, crushing, and/or shear cracks. Thermal imaging of the cracks will show warmer spots where material is crumpled or sheared, interrupting heat flow. Then there's tension stress. Imagine pulling a rope from both ends. That's tension stress in action. It's the force that stretches and pulls, often applied to structural components like beams and shafts. Tension is the cause, while tensile stress is the effect. Tensile stress measures the internal force per unit area that builds up as the material stretches. It's the strength test. How much pulling force can the material handle before it deforms or breaks? Tensile stress may cause longitudinal cracks, necking, and fracture. Thermal imaging of the cracks will have cooler regions along the crack lines due to reduced thermal conductivity. Now, let's look at bending stress. Picture a ruler balanced on a table edge, and you press down on the overhanging part. The force you apply creates bending stress within the ruler, causing it to flex and bend under the load. Cracks from bending stress occur at stress points. Thermal imaging of components undergoing bending stress will have localized hot spots or cold spots, depending on the thermal conductivity and material properties affected by the bending stress. Another key player is torsional stress. This is the stress that happens when you twist an object. Think of turning a doorknob or twisting a towel. That twisting action creates torsional stress. Torsional stress results in spiral cracks or twisting fractures. In thermal imaging, we'll show spiral thermal patterns following the twist direction. Finally, we have shear stress, a force that makes parts of a material slide past each other in opposite directions. Imagine scissors cutting paper. The blades create shear stress on the paper, forcing it to shear and separate along the cutting line. Cracks created from shear stress will be diagonal and along the slip planes. Thermal image shows distorted thermal patterns, often diagonal or at joint areas. Each of these stresses plays a crucial role in understanding how materials behave, whether they're under pressure, being stretched, bent, twisted, or sheared. Recognizing these stress types helps engineers design stronger, more resilient structures to handle the demands of the real world. Different types of cracks and their distinguishing features. Let's dive into the world of cracks and breaks in materials, each with unique characteristics and causes. Starting with radial cracks, these cracks radiate from the surface toward the center, like spokes on a wheel. They're thin, extending inward, and are often caused by high stress concentrations, impact, or thermal stress. Radial cracks are usually linked to fatigue or thermal stress. This may be caused by improper maintenance, material quality, extreme temperatures, or temperature changes. Next, we have transverse cracks, which run straight across the shaft's diameter, perpendicular to its length. These cracks are often caused by bending stresses or impact and can be a sign of material defects or misalignment. Transverse cracks may be caused by overloading, impact or shock loads, corrosion, material defects, or fatigue. Moving on to oblique cracks, these are angled relative to the shaft axis, appearing diagonally or at a slant. Oblique cracks often occur due to combined bending and torsional stresses, frequently associated with material defects or fatigue. Oblique cracks are compression or torsional stress. They are a combination of bending and torsional stress. This occurs due to material fatigue, design issues, or impact loads. Longitudinal cracks are another type. These cracks run parallel to the shaft's axis, stretching along its length. They're commonly caused by torsional stresses or residual stresses from manufacturing processes. Longitudinal cracks occur from internal pressure, material defects, stress concentrations, corrosion, fatigue, cyclic loading, and temperature variations, thermal stress. Then we have torsional cracks. These cracks form a helical or spiral pattern around the shaft, caused by excessive twisting or torque. Improper alignment or sudden stops can also lead to torsional cracks, typically associated with fatigue. Next, let's discuss brittle cracks. These cracks are rare but dramatic, showing a clean, sharp break with minimal deformation. Brittle cracks are often a result of low temperatures or high strain rates and are associated with material brittleness. Ductile cracks appear rough and fibrous, with significant plastic deformation. They often occur in high ductility materials subjected to heavy loads or gradual overload. Fatigue cracks develop over time due to cyclic loading. You might notice beach marks or striations on the surface, showing the repetitive nature of the crack growth. Stress corrosion cracking, or SCC, is a unique type where cracks form from a combination of tensile stress and corrosive environments. These appear as branched, intergranular cracks with evidence of corrosion. Thermal cracks are the result of thermal stress due to rapid temperature changes or gradients. Thermal cracks often have a transverse or perpendicular orientation to the direction of thermal expansion or contraction. In some materials, especially metals, they may form a crazed or spiderweb-like pattern, particularly when the surface expands unevenly. In ceramic and glass materials, thermal cracks can appear as sharp, brittle breaks, often radiating from a specific point where temperature fluctuation was most extreme. These cracks often appear at points of high thermal stress, particularly when the material faces extreme temperature differences. Understanding these different types of cracks, from their appearance to their potential causes, is crucial for diagnosing material failures and improving design resilience. Each type tells a story about the forces the material has faced and helps engineers predict and prevent future issues. Production environment, location, and causes. Torsional stress is the stress produced when a material is subjected to a twisting force or torque around its axis. Imagine twisting a rubber band in opposite directions at both ends. That's torsional stress in action. This type of stress is particularly common in shafts, axles, and other rotating components where twisting forces are frequently applied. Appearance. When torsional stress is present, it often manifests as shear stress along the material. In cylindrical parts like shafts, the stress increases as you move farther from the center axis, meaning the outer edges bear the highest stress levels. Over time, if torsional stress exceeds the material's capacity, it can lead to the development of small cracks, often at a 45-degree angle to the axis. These cracks can spiral along the length of the component, and in severe cases, the twisting forces can cause complete fracture with a characteristic helical or corkscrew pattern on the broken surface. Torsional stress is common in drive systems and axles, rotors and motors and generators, propeller and helicopter shafts, gears and gearboxes, camshafts and crankshafts, conveyor systems, wind turbine shafts, drill strings in oil and gas drilling, power transmission belts and chains, flywheels, mixing equipment, extrusions, and processes with variable loads, caused by a twisting force applied to the shaft. Excessive torsion can initiate cracks due to the shearing stress exceeding the material's strength. Understanding and managing torsional stress is crucial, especially in applications with rotating machinery, as excessive stress can lead to component failure and costly downtime. Bending stress. Bending stress occurs when a force is applied to a material, causing it to bend around an axis. This stress acts perpendicular to the material's cross-section, leading to tension on one side and compression on the other. Imagine forging a metal rod as the rod is bent. One side stretches, while the opposite side compresses. This is bending stress at work. It's especially common in beams and girders in construction. Crane booms and lifting arms, levers and crowbars, cantilever beams and structures, structural frames and supports, vehicle chassis and frames, railway tracks and rails, wind turbine blades, airplane wings, mining and evacuation equipment arms, pipes and pipelines, and electrical transmission towers. Appearance. In materials under bending stress, you'll often observe curvature or deflection. The side under tension may begin to elongate, while the side under compression may shorten or even form slight ridges. If the stress exceeds the material's limits, cracks can develop on the tension side, especially near points of maximum bending, like the middle of a beam. These cracks may run perpendicular to the length of the material and, if left unchecked, can lead to full fractures or breakage. Understanding bending stress is essential in designing and inspecting structures, machinery, and support beams to prevent failure and ensure safety. Axial stress. Axial stress is the stress exerted on a material along its axis when a force is applied parallel to its length. This type of stress occurs when a material is either compressed or stretched in a straight line, creating either tension or compression within the structure. For example, a cylindrical metal bar undergoes tension along its length as axial force is applied at both ends along the bar's axis. The bar begins to elongate as stress is applied over time. Appearance. In materials under axial stress, the effects can vary based on whether they are under tension or compression. In tension, you may see a slight elongation, thinning, or necking of the material as it stretches. Under compression, the material may shorten and can potentially bulge or buckle, especially if it is slender or lacks lateral support. If the axial load is excessive, it may lead to fractures, with cracks often running parallel to the material's axis. Common in equipment. Axial stress is prevalent in equipment like columns, rods, bolts, and cables. Structural columns in buildings bear axial compression under load, while bolts in assemblies face axial tension as they secure components together. Axial stress is also seen in suspension cables of bridges, which support weight through tensile stress along their length, and in drive shafts or pistons where compressive and tensile forces act along the axis of motion. Managing axial stress in these applications is essential to prevent buckling, breaking, or deformation that could compromise the integrity of the structure or machinery. Fatigue stress. Fatigue stress is the stress that results from repeated loading and unloading of a material over time. Unlike a single, powerful load, fatigue stress develops gradually as the material experiences cycles of stress that can cause small, progressive damage. This repeated loading eventually leads to microscopic cracks that grow and weaken the material. Fatigue stress is a common cause of failure in components subjected to continuous or cyclic loads. Appearance. Fatigue stress manifests as small, microscopic cracks that usually start at points of high stress concentration, such as edges, corners, or surface imperfections. Over time, these cracks propagate, often creating visible fracture lines that follow a distinct pattern called striations, across the fracture surface. Eventually, the material reaches a point where it can no longer sustain the stress, leading to a sudden and complete break, even under relatively low loads. Common in equipment. Fatigue stress is particularly common in equipment that undergoes repeated cycles of stress, such as aircraft wings, rotating shafts, gears, and suspension components. In aircraft, wings flex repeatedly due to varying aerodynamic forces, making them prone to fatigue stress over time. Rotating shafts in engines, gearboxes, and drive trains experience constant cycles of tension and compression, which can lead to fatigue cracks. Suspension components in vehicles, exposed to regular impact and vibration, are also susceptible. In addition, machinery like pumps, compressors, and turbines, which operate continuously, face fatigue stress in moving parts due to vibration and cyclical loading. Understanding and managing fatigue stress is critical to ensure the longevity and safety of equipment, as fatigue-related failures are often sudden and unexpected. Thermal stress. Thermal stress occurs when a material experiences a temperature change that causes it to expand or contract. When different parts of the material heat up or cool down unevenly, it creates internal stress. This can happen within a single material or where different materials meet, as each one expands or contracts at different rates. Thermal stress is common in equipment exposed to rapid or extreme temperature changes, and if left unchecked, it can lead to warping, cracking, or even complete structural failure. Appearance. Thermal stress often appears as fine, web-like cracks on the surface of the material, especially in areas where temperature changes are most intense. In metals, these cracks can show a distinct pattern, often perpendicular to the direction of thermal expansion. Over time, these small cracks can grow deeper, potentially leading to fractures. In ceramics and glass, thermal stress can create sharp, brittle cracks that spread rapidly, especially around points where heat was applied or removed unevenly. Common in equipment. Thermal stress is frequently seen in equipment such as furnace components, exhaust manifolds, boilers, and engine cylinders. Furnace parts, for example, undergo constant heating and cooling cycles, leading to thermal fatigue and cracking. Exhaust manifolds in vehicles experience rapid heating from engine exhaust gases, which can cause cracking over time. Boilers and pressure vessels exposed to high-temperature steam are also at risk, particularly near welds and fittings. In electronics, circuit boards and components can develop thermal stress from repeated heating and cooling cycles, leading to microcracks in solder joints and other delicate parts. Managing thermal stress is crucial to ensure the longevity and safe operation of equipment, as unchecked thermal expansion can lead to critical damage and failure. Corrosive stress. Corrosive stress is the stress experienced by materials exposed to corrosive environments, where chemical reactions weaken the structure over time. This stress is particularly problematic because it involves a combination of mechanical stress and chemical attack. When materials like metals face constant stress in corrosive environments, such as saltwater, chemicals, or acidic conditions, corrosive stress accelerates, causing structural degradation much faster than from either factor alone. This process is known as stress corrosion cracking. Appearance. Corrosive stress often manifests as fine, branching cracks or pits on the material's surface, particularly in areas under mechanical stress. These cracks typically begin as small surface flaws but deepen over time, creating branching patterns and leading to brittleness. The material may show visible signs of corrosion, such as rust, discoloration, or surface roughness. In severe cases, these cracks propagate quickly and can lead to sudden, brittle failure without much warning. Common in equipment. Corrosive stress is frequently found in pipelines, marine structures, storage tanks, and chemical processing equipment. Pipelines carrying corrosive fluids or exposed to moisture and soil conditions are at risk of stress corrosion cracking, especially in high-stress areas like bends or welds. Marine structures, such as offshore platforms and ship hulls, face corrosive stress due to constant exposure to salt water and wave impact. Storage tanks for chemicals and acids are also vulnerable, particularly near joints and connections under stress. Additionally, in refineries and chemical plants, Equipment exposed to aggressive chemicals at high pressures and temperatures faces significant corrosive stress, demanding regular inspection and maintenance to prevent unexpected failures. Preventing and managing corrosive stress is essential to ensure the longevity and safe operation of equipment, especially in harsh environments, as stress corrosion cracking can lead to sudden and catastrophic failure. Impact stress. Impact stress is the stress experienced by a material when it undergoes a sudden force or shock. Unlike gradual or cyclic loads, impact stress results from an abrupt, high-energy event, such as a collision or blow. This sudden force causes intense, localized stress, which can lead to material deformation, cracks, or even complete failure. Materials and structures that aren't designed to absorb or distribute this type of stress can fracture easily under impact. Appearance. Impact stress often appears as visible cracks, dents, or fractures in the material, with cracking usually localized around the point of impact. In brittle materials, impact can cause sharp, sudden breaks with jagged edges. In metals and other ductile materials, the impact may leave indentations or signs of bending or deformation near the affected area. In severe cases, the material may fracture completely, breaking into distinct sections. Common in equipment. Impact stress is common in tools, vehicle bumpers, structural beams, and machinery components. Hand tools, such as hammers and chisels, are designed to withstand impact but can still develop stress fractures over time with heavy use. Vehicle bumpers and crash structures are specifically built to absorb impact stress from collisions, helping to protect occupants. Structural beams and support columns may encounter impact stress from falling objects or equipment collisions on construction sites. In machinery, rotating parts or gears may occasionally jam or collide, leading to impact stress in the affected components. Additionally, drill bits, mining equipment, and other tools in contact with hard surfaces experience repeated impact stress, making them prone to cracking and wear. Effectively managing impact stress is crucial in designing equipment and safety systems, as it ensures materials can withstand sudden shocks without failing catastrophically. Creep stress. Creep stress refers to the gradual, time-dependent deformation of a material under constant stress, particularly at high temperatures. Unlike sudden or immediate deformation, creep happens slowly as materials stretch or deform under a sustained load over time. This type of stress is common in materials exposed to prolonged stress at elevated temperatures, where the atomic structure slowly shifts, resulting in permanent deformation. Appearance. Creep stress typically appears as elongation or warping of the material, often around areas that experience continuous loading. In metals, the surface may show slight bulges, thinning, or even visible deformation in high-stress zones. Over time, creep can lead to small cracks or voids within the material, especially at grain boundaries. As the material continues to deform, these microcracks can grow, eventually leading to visible fractures or even complete failure. Common in equipment. Creep stress is especially common in boilers, steam pipes, turbine blades, and furnace components. Boilers and steam pipes operating at high pressures and temperatures experience creep in areas exposed to continuous heat and load, like pipe bends and weld joints. Turbine blades in gas and steam turbines face high temperatures and rotational stress, making them susceptible to creep deformation and cracking. Furnace components, like heat exchangers and refractories, also endure sustained thermal stress, leading to creep over time. In power plants and chemical processing facilities, creep stress in high-temperature equipment requires careful monitoring and periodic inspection to prevent unexpected failures. Understanding creep stress is crucial for designing equipment that can withstand long-term, high-temperature conditions, as it helps prevent deformation and extends the life of critical components. How thermal imaging detects cracks in industrial equipment. Now that we've learned about stress and their impact on component parts, let's explore how the power of thermal imaging helps us identify hidden cracks in materials. When a material has a crack, it disrupts the normal flow of heat. Imagine heat moving uniformly through an intact material. But when there's a crack, this heat flow is interrupted, creating irregularities in temperature distribution. In the heating phase, as the material warms up, the area around the crack may absorb and retain heat differently than the rest of the material. You might see this as a hot spot or a cold spot, depending on how the heat flows. Then comes the cooling phase. When the material cools, the region around the crack will cool down at a different rate. This unique thermal behavior creates a temperature gradient, or a visible difference in temperature, around the crack. This thermal gradient is the key. Using a thermal imaging camera, we can detect this pattern and pinpoint cracks that may not be visible to the naked eye. By analyzing these thermal signatures, we can identify potential weaknesses and prevent material failure before it occurs. Understanding temperature gradients in components. Let's dive into the fascinating science of temperature gradients in components and how stress affects them. Stress is a measure of a material's internal resistance to deformation. Every component has unique features, and each feature exhibits its own characteristic stress. Understanding these stress points can reveal a lot about a component's integrity and potential points of failure. Take a line shaft, for example. This shaft might have various stress-inducing features like step-change locations, where there's a sudden shift in geometric shape, marked by factors such as _X. Keyways, which are drilled holes used to secure gears or pulleys, bearing locations, which carry loads and can be subject to misalignment, and finally, threads, notches, or surface defects. Each of these features creates a different stress concentration, which in turn affects the temperature of that area. During thermal imaging, these changes can appear as distinct temperature variations or thermal gradients. For instance, areas with higher stress may show up as hot spots, while less stressed areas remain cooler. Corrosion, surface defects, or pitting can initiate these changes and disrupt the thermal pattern we observe. By analyzing these temperature gradients, we gain a deeper understanding of stress distribution within the component. This information is invaluable for detecting issues before they lead to potential failures. Thermal imaging, then, becomes not only a diagnostic tool but a preventive measure in maintaining the health and longevity of our components. Thermal signatures of cracks. Throughout this video, we've examined several types of stress that lead to different kinds of cracks, each with its own thermal signature. These signatures, detectable through thermal imaging, help us identify the location and nature of potential weak points. We've also seen how various structural features within a component, like keyways, notches, threads, and step-change locations, create unique areas of localized stress. These regions show up as distinct temperature differences on a thermal image. But here's the big question. How do we distinguish between thermal signatures caused by external stress loads versus those caused by internal, localized stress within the material itself? External stress loads typically affect the entire component, resulting in broader thermal gradients across the material. This type of stress may cause uniform changes in temperature or large-scale patterns that cover a wider area. In contrast, internal localized stress from features like notches or threads usually results in specific, concentrated temperature differences around those points only. By analyzing these thermal patterns in detail, we can identify whether the heat signature is from a widespread load affecting the entire structure or a localized stress concentration caused by design features. With experience and the right techniques, thermal imaging allows us to accurately pinpoint these areas, making it an essential tool for proactive maintenance and component analysis. Detecting stress corrosion cracking, SCC, using thermal imaging. Thermal imaging is a powerful tool for detecting different types of corrosion, each leaving unique thermal signatures. Let's walk through these types of corrosion and understand how they appear on a thermal image. Starting with internal corrosion, such as pitting and uniform corrosion. Uniform corrosion, which affects a broader area, usually appears as a gradual temperature gradient across the corroded surface, creating a more diffuse thermal pattern. External corrosion comes in many forms. Microbial influence corrosion, or MIC, often displays as irregular thermal patches with distinct cold spots or areas of uneven heating. This is due to microbial colonies causing localized reactions on the surface. Oxidation under deposition is next. This type of corrosion happens beneath a layer of contaminants, leading to thermal irregularities that are more spread out. You'll likely see patches of varying temperature where oxidation disrupts the thermal flow beneath the deposit layer. Hydrogen-induced cracking presents itself differently. This internal corrosion can create faint, cold lines or cooler zones along the crack path due to the disruption of material integrity, which affects the heat flow. Stress corrosion cracking and cracking are both types that can form hot spots in thermal imaging. These hot spots indicate areas of high stress concentration, where the material is weakened and prone to crack propagation under thermal stress. Embrittlement, a condition where the metal becomes brittle, can also appear as hot or cold spots, depending on where the embrittled material alters heat distribution, often showing inconsistent temperatures along the affected region. Lastly, flow-induced corrosion. This form of external wear is often visible as a high-temperature gradient in areas where fluid flow causes accelerated material degradation. It may appear as a hot zone in the direction of flow, highlighting regions experiencing higher levels of wear. In thermal imaging, each type of corrosion, whether internal or external, has a unique thermal signature, from hot spots to gradients and cool zones. Recognizing these patterns helps us accurately identify and address corrosion before it leads to component failure. In this video, we've covered a lot of ground, from identifying different types of stress and the cracks they cause to understanding their unique failure mechanisms and, most importantly, using thermal imaging to detect these issues early, preventing unexpected downtime. We hope you found this information valuable and that it helps you in keeping your equipment running smoothly. If you enjoyed this video, please like, share, and subscribe to stay up to date with more insights like these. Thanks for watching, and until next time.